Recording. I think this should work now. So with that, Simon, the screen is yours.
Great. Chris, thank you very much for the invitation to speak here today, and it's a pleasure to be here. My topic is how AI agents are transforming battery research, and I think it's a really uh, timely topic because things are starting to move so fast in this field, and I think it's really going to change how we do battery research, especially any kind of simulation or digitalization battery research in a fundamental way, which is exciting and a little bit scary, but hopefully more exciting. So, in my talk, I will take you through some of the background for how we got to this point and some of the foundational developments that we continue to build on. And then I'll talk a little bit about the individual pieces that help to make this possible today. And at the end, show some exciting new results that have really just come out over the last few weeks to demonstrate the potential for AI agents in battery research. Great. So yes, my talk today is divided into four parts. We'll start with a little bit of background, both theoretically and looking at some success stories from other fields that we can try to learn from as we seek to implement something similar for batteries. Then we'll talk a little bit about battery virtual environments and semantic technology that are key enabling parts for integrating agents into our research and into our work. And then finally end with some demonstration of agentic workflows. Great. So some background on agents. If I had to summarize where we are today in the AI agent workspace, it reminds me of a quote from Sherlock Holmes. When I was a kid, I used to love the Sherlock Holmes books. I think I've read every one that's ever been published. And in one, there's a scene where Sherlock Holmes is rummaging around the crime scene, and frustratedly he calls out, "Data, data, data," he cried impatiently. "I cannot make bricks without clay." And I think this is representative of the AI space that we're working in today because the engines have become so powerful and the agents have become so flexible and have such potential that really they are not the bottleneck anymore. The bottleneck is having data to train from, having data to learn on, and having data to process and to work in interesting ways with. So we're really facing more of a data bottleneck than anything else. And the basis for the talk that I'm going to give today was actually given 9 months ago at the Polis seminar. And I think it's interesting to highlight how quickly things have changed in only 9 months. So if you're not familiar with AI or if you don't really follow the field so closely, it may be kind of a new term for you. But in 2024, terms like third wave AI or agentic AI started to become really popular buzzwords. That these are going to transform the way we work. It's going to transform financial services. It's going to change how businesses deliver their services to customers. And whereas only 9 months ago, this seemed like, okay, well, it's just another fad, another kind of trend. Today, we can really see it integrating into our everyday work environments. And at least for me personally, it's something that I use every single day. But what do we mean when we say AI agents? How is that really different from a chatbot or from any other AI system? And we can summarize it in this way. Chatbots like ChatGPT are reactive and interact with the user through a kind of flat interface. They're based on call and response interactions. So a battery researcher may say, for example, what is a good anode material for lithium-ion batteries? And the chatbot will respond, graphite. It's a good anode material. Easy peasy. And that's helpful. But in most of our real work, we need to undertake more complex actions. And agentic AI starts to enable that. So agentic AI understands goals, it makes plans, it takes initiative, uses tools, and can even interact with other agents in order to complete complex tasks. So whereas in a simple chatbot example, the researcher may ask what's a good anode material. With agentic AI, you can give it more complex tasks like evaluate if our silicon graphite anodes are suitable to reach the cell KPIs for generation 3B batteries with LNMO. And that may require the agent to query a database, get back some tables, do some processing on it, maybe do some simulations based on the cloud and retrieve some analytics in order to give you back an answer. Yes, it's good enough, or no, it's not. And that requires awareness of all of the tools and all of the resources that it has available to it, as well as understanding of the different systems, the meaning of the data that they contain, and perhaps most importantly, how to exchange information across those interfaces and across the different tools. So if we want to understand a little bit of the history of how we got here and what some of the core developments have been, it's easy to look at this and say, well, this is something totally new. This is something we haven't seen before. And maybe in some ways true, but like we say, there's nothing new under the sun. And really, the developments that we see today have their roots going back more than 20 years to something called the semantic web. And the semantic web was an extension of the World Wide Web, originally developed at CERN in Switzerland for managing research data. And what they found in the early development of the World Wide Web is to say, okay, we can link different assets. We can say this hyperlink points to that document, but it doesn't tell us anything about what those documents are or what information they contain or how anybody should interact with it. And so the founders of the World Wide Web came up with this idea called the semantic web, which is an extension of the World Wide Web to give information well-defined meaning to better enable computers and people to work together in cooperation, which is really what a lot of agentic AI is about. And if we go all the way back to the original article that was published presenting this concept, we actually don't have to look very far to find agents described prominently in the plan for the system. And agent may be unfamiliar terminology to many people who aren't so deep in the field. But when we say agent, we're describing a software entity that acts autonomously on behalf of a user or another system using some structured, semantically annotated data and web standards to make decisions and coordinate actions. And we can understand immediately that there are kind of two aspects to that. On the one hand, there's the ability to understand the data and to understand the systems that they're encountering. And on the other hand, there is the agency to take actions, to process it, and to do something useful with it. So if we take the first part of that, how does an agent understand the meaning of the data that it encounters? We also don't have to go very far from the original plan of the semantic web. Actually, just above, whoops, going the wrong way. There we go. Just above to get to ontologies. Now, an ontology is a description of a domain that formally defines the relationships among terms, describing knowledge in a machine-readable way. And the most typical kind of ontology for the web has a taxonomy, which is a kind of hierarchy of terms, and a clear set of inference rules. And those have been extremely well developed for many general knowledge topics on the web. They include things like search engine optimization, but they can be slow to reach the scientific or technical domains, even though they're essential to enabling AI in the battery space. So if we want to learn from that, how can we start moving towards the vision of having AI agents who are not only able to, book you a ticket on an airline website or to find you the nearest restaurant, but to actually make scientific progress within battery science. So we have very good tools for an infrastructure for humans to interact with machines through natural language interfaces. But so far, what we have been lacking is the extensive networks of data and tools for agents to work with. And I think that has been true up through the last few years until the last year or so. And I've been working in this field for about 7 or 8 years, and I have the feeling that it's kind of like riding a roller coaster, that we've been developing over the last 7 or 8 years, databases and standards and simulation environments and all of the little pieces that we need in order to bring this to fruition. And only now are they really starting to come together to form a coherent system that agents can act on and participate in, and is really starting to open up some interesting opportunities that I'll highlight. But before we get into batteries, maybe it's good to first look at other fields and see how they have managed to use this and how they've managed to develop it, and try to see what lessons we can take away from that for building our battery infrastructure. So we can ask ourselves the question, what happens when agents have access to the data and to the virtual environments that they need? If we can wave a magic wand and create a magic world where all of the databases and all of the virtual environments exist, what can it do? And again, we can look to the past, to 2010, for example, when a company called DeepMind was founded in London with the goal to develop artificial general intelligence. And they started off in a kind of unusual place, which was to develop an agent to play games. And they started with Pong. And what they found was by giving the agent access to the Pong video game and telling it nothing other than the fact that scoring is good and giving a high score, after many thousands of failed games, it eventually gets to get the idea of the game and conquers the game of Pong. And gave it something a little bit more tricky, like the game Breakout, again, telling it nothing about the environment, just how to control the paddle, and that scoring is good. And it finds this strategy to break a tunnel around the sides and put the ball around the back. So already starting to show some problem-solving capabilities. But then in 2016, they gave it what was considered to be one of the toughest challenges that artificial intelligence can solve, which is the game of Go, and challenged one of the world leaders at the time, Lee Sedol, to a game of Go. And what they found was that it would occasionally play these moves that, to all the experts, appeared to be mistakes, and kind of confounded even the most professional players and gave the development team a heart attack. But eventually, AlphaGo ended up winning the match and showing that these kinds of moves that humans don't understand, these moves that humans think are mistakes, can actually lead to different outcomes and unexpected results. So trained on games, kind of a silly example, but interesting. and ultimately laid the foundation in 2024 for applying the same methodology to solving the problem of protein structures and being able to predict protein structures from their compositions, which won the 2024 Nobel Prize in Chemistry. So over a period of 14 years, developing AI agents and giving them access to the environments and to the data infrastructures that they need to learn from and to work on, went from playing bad games of Pong to winning the Nobel Prize in chemistry, which I think is interesting and instructive. So if we want to think about how we can start applying similar approaches in batteries, and how can we open battery science, which is also notoriously complex and difficult, to simpler workflows, we can learn from this and say, okay, well, there are two things that really enable this to happen. One is good virtual environments for doing simulations and for evaluating the effects of changes and supporting reinforcement learning. And the second is extensive, deep, well-structured data infrastructures containing semantic annotations. So with that, we can start bringing it into the battery space and to try to get a feel for recent developments that are enabling us to bring this into battery science. And the first one I'd like to highlight is battery virtual environments. So by virtual environments, I mean simulation tools where agents can play with changes in materials, changes in cell design, and evaluate how that affects performance with some KPIs. And I think physics-based battery models are a really good way to do that, and especially the continuum modeling approaches that have been pioneered by Newman et al. Are the kind of gold standard for physics-based models today. If you're not familiar with those approaches, they basically allow us to discretize complex battery geometries into a set of finite volumes or finite elements where we can solve the continuity equations for concentration and electric potential and temperature across the cell domain, and basically allow us to kind of peek inside the battery to understand how local conditions are changing to affect the macro performance of the battery. And up until 7 or 8 years ago, if you wanted to build a model like this, if you wanted to run a simulation, you basically had to do it yourself. You had to sit down and write your own Python code or write your own MATLAB code, and it was extremely intensive to do. But luckily, the developments in the open source community have been really robust over the last few years and have allowed us to develop rich simulation environments that agents can have access to work in these kinds of fields. So on the one hand, we have a lot of open source solvers for these models that have become available starting around 2019 or so. Of course, PyBAM, which is very familiar in Python. We also have Batmo, which is in MATLAB and Julia, and CityMod, which is an extension of Phoenix, among others. So really, the engines to solve these simulations exist, and we can build on those. We've also done a whole lot of work to improve speed, which if you want to do not only 1 or 2 simulations, but thousands of simulations starts to become important. In 2019, when we started, maybe doing one simulation of a cycle would take about 10 seconds. And now it's down to 100 milliseconds or less, so it's essentially instant. And that opens up a lot of interesting opportunities for doing large parameter space exploration and variation. More recently, there's been a lot of work on parameter calibration and design optimization. Like any physics-based model, we really rely a lot on extensive parameter sets that can be difficult to measure. And so these methods start to reduce the burden of parameterization and be able to extract as much information from our test data as we can without doing excessive testing. And starting to move towards exchange standards. So once we have those parameters, we can move in between environments. And within the last year or so, starting to build in semantics and AI agents to move from the realm of a human sitting at a computer and building a simulation to a human giving an AI agent a complex task and leaving it to solve it on its own. We'll see an example. But yeah, one of these environments, which I'd just like to highlight, this is one that we developed at SINTEF, is called BATMO, which is short for the Battery Modeling Toolbox, and it implements the PXD Newman model in Julia and MATLAB. Developed mostly for lithium-ion batteries, but we also do sodium-ion, metal air, and even electrolyzer combinations. Exists as part of a larger ecosystem. So on the one hand, we can do physics-based self-performance models using the DFN model to evaluate how will a certain material or how will a certain design perform. That then links with techno-economic models to say, okay, we have a good cell, how much will it cost to manufacture 1 billion of them on a gigafactory scale? And linking that with semantic data resources to try to create a holistic system for an agent to respond to complex queries. Yes, and so BATMO basically discretizes our electrochemical cell, seen here from our negative electrode, separator, and positive electrode, into a set of finite volumes and solves the continuity equations on that grid. And that allows you to basically look inside and see how profiles like temperature and concentration and electric potential develop in order to see not only the macro scale, things like capacity, fade, or cell voltage, but to better understand what it is exactly happening inside the cell that drives that performance. Great. So with BATMO or PyBAM or CityMod or any number of these tools, we now have our virtual environments that agents can use to evaluate different cell designs. But still, we need the semantic infrastructure for agents to understand what kind of data they have access to and how they can use it and how they can interface with these different systems. I think one of the things that I would like to highlight, especially here in a more material science environment, is the importance of publishing data and what types of things that starts to enable if we do. Of course, in scientific research and in European Union projects and things, there's always the push to publish data, to do fair data infrastructure, and it's seen, I think, as kind of an extra burden. Like, oh, we're all so busy already. How can we take the extra time to do these things? Which is true, but I think it's the how can I say the things that it opens up are so much bigger than the burden of actually publishing things, and I'll show you an example of it. So here, for example, if you are to talk to a chatbot about things that it has general access to, like stats data from sports or finance or pop culture, it can respond extremely well. But it really struggles with battery data queries. For example, if I ask ChatGPT to predict the open circuit potential profile of graphite, it's one of the most important materials in batteries, it gives us the blue curve here, which is totally wrong. The actual curve is in pink here. And part of the reason for this, I think, is that when we look into how many data sets have been published that provide the OCP profile for graphite in an open way with the source data and a permissive license. It's only 6. The most common material in all of lithium-ion batteries, one of the most important parameters that's quite easy to measure. Extremely small data sets that have been published. And so if we can break beyond that, if we can start to say, okay, you know, the more data that we can contribute to these infrastructures, the more resources we have to learn from, the better these agents are going to be, the more accurately and the more powerfully they're going to be able to help us and respond to our queries. I think it starts to open up a interesting world. And so to do that, we can start to create a semantic infrastructure to help make that easy and help machines to understand the data that does exist. And within semantics, we have a kind of stack of tools that we use to attach meaning to data. Fundamentally, we build on the World Wide Web standards, which define efficient ways for expressing meaning and sharing information about things. And the semantic web is something that we interact with every day. On top of that, we can create controlled vocabularies, which act as a kind of dictionary that give terms a controlled meaning that both humans and machines can interact with and understand. Ontologies then exist as a extension of that also define the relationships between terms and formalize all of the knowledge about a domain. And once we start implementing real examples and real instances, we can create a knowledge graph that ultimately is the foundation for linked data, which AI agents need to understand and to learn from. So over the last 7 years or so, we've been implementing this whole technology stack for batteries. And it's only now really starting to come to fruition and starting to pay benefits for battery research. And one of the core resources that we've developed is an ontology for batteries and describing this information for both people and machines. And a kind of comparable example is schema.org, which was developed by Google and Microsoft for describing things that people tend to search for and enabling search engine optimization. So in schema.org, they may describe a person, and that person is a node, which is connected to its name by a property. Maybe this person has a nationality, which links it to some country. And if this person is an athlete, maybe he is on some sports team. So systems like this are the reason why AI agents are extremely good at responding to general knowledge queries. And we've been developing the same kind of infrastructure for batteries. So instead of describing a person, we can describe an electrochemical cell that has a negative electrode, some electrode, that has an active material that is in contact with some electrolyte, and start to provide a kind of framework or foundation for machine agents to understand the nature of things and how they're connected to each other. So by implementing all of this together, we can create a kind of semantic web for batteries that is able to be navigated by people and machines. And as I mentioned, bioinformatics and proteins is one of the areas of science that have really used this to extraordinary effect. All the way back in the 1970s, laying the foundation for really good data management and really good semantic infrastructure. So that when DeepMind and AlphaFold came along and wanted to find a high impact problem to train on and a high impact problem to solve, they had 50 years of data and 50 years of good infrastructure to learn from. And we've seen what's been possible with that. So I think if we can learn from this for batteries, it can open up a lot of interesting worlds for us. And one of the challenges is that proteins and genes is a relatively limited scope. But material science is just the opposite. Material science is everything. Material science is physics and chemistry and thermodynamics and manufacturing and engineering. And it requires a really well-grounded, flexible, and logical and consistent framework to describe not only one of these little aspects in an internally logically consistent way, but everything in a way that can link together. And that has been extremely difficult to do because these domains have to form stable links. And if they don't, then any kind of little wobbliness in the structure is going to bring the whole thing down. And that has been the biggest challenge that we faced in bringing these approaches in material science. But luckily, the EMMC has invested a lot in the development of EMMO, the Elementary Multi-Perspective Materials Ontology, and that has provided a really stable foundation for us to extend to describe not only chemical substances and electrochemistry, but also batteries, so that we can have the semantic infrastructure that we need for these systems to learn from and operate on. So, to start to come to the interesting part, what can we do once we have done this? Once we have spent years developing infrastructure and developing agents and developing virtual environments, how can we start to put this to good use in our day-to-day life? Basically, as we mentioned in the beginning, the real power of agentic AI is being able to respond to complex queries and take actions across different systems in order to achieve some goal. So in a simple case where we want to retrieve some results from discharging a coin cell, for example, we give that prompt to a user interface layer, which has some endpoint, which interprets that information and interprets the systems that it has access to through some ontology and associated knowledge graph, and can then work across our data layer in order to get that information and take action on it. And depending where you are on this scale, you can work on different layers. So ontology and knowledge graphs and things, they're not for everybody, more for developers and data stewards, but for general researchers, we can stay at this top level just using tools. So now that we have some background, now that we have an understanding a little bit of the individual pieces that exist in order to bring all this to fruition, I'd like to show some examples of how this can be applied and how this can be used in real agentic workflows. So recently, what I have been working on is incorporating agents based on a combination of models, including Codex and Claude and Gemini, into battery virtual environments that have access to BATMO as a simulation resource and the battery interface ontology as a semantics and data registry. And that allows us to give very simple natural language prompts and get complex results out from them. So, for example, if you're familiar with battery simulation or the Newman model, you may be familiar with the CHIN 2020 parameter set, which is a kind of benchmark for doing battery simulations. So one of the first examples that I tried was to say, well, let's just recreate the CHIN 2020 benchmark. So I gave my agent the prompt, simulate one CCCV charge discharge cycle using model parameters from CHIN 2020. I want it to have these particular parameters for the charging and discharging cycle, then rest. And when the simulation's finished, give me the cell voltage and the different contour plots on the dashboard. So on the one hand, a complex task, because it has to pull information from different things and to do, understand what I'm asking it, but still relatively simple. But it did it perfectly and quickly. It gave me exactly what I wanted, retrieved exactly the parameters it was supposed to, set up the cycling procedure that I gave. If you're a battery person, you recognize this as a charging, CV hold, rest, discharge curve. So yeah, the first hurdle passed, easy peasy. And yeah, also gave me all of the state variables that I needed. And so, whereas this procedure beforehand would have involved me opening a JSON file and manually changing some parameters and sending it to the simulation environment, saying, okay, this plot isn't the way I wanted it. It takes care of all of that for you and does it behind the scenes. So that's great, but that's still a pretty easy example. Let's up the stakes. Let's try something a little harder. Here is some data that was measured from an actual battery cell, experimental data in the 10-20-20 data set. Analyze it, then run a model under the same conditions in order to show validation. And I gave it a link to the Zenodo file where that data is stored. And again, practically perfect. Retrieved the data from Zenodo, extracted out the cycling protocol, simulated that in Batman, and then gave me this comparison of discharge curves at the different currents from the experimental data, with an overview of the errors, relative errors between the two systems. Great. Okay, well, let's try something even harder. Oh, yes. And then also, so we can say okay, well, this is an extremely good fit, but it's not perfect. Analyze this and give me recommendations for what other tests I can do in order to improve the parameterization. He says, well, okay, let's look at it. So your RMSE values are very low for low rates. That means that your cell balancing and equilibrium behavior is reasonably good. But once you start going to higher rates, you get more error. So that means that your kinetic and transport parameters are not so good. You should do some HPBC at several SOC points to separate the ohmic and kinetic losses. You should do some GITT or pulse relaxation measurements to get the solid diffusion and electrolyte transport parameters, which from a kind of expert perspective is exactly what I would do and exactly the approach that I would take. So on the one hand, being able to interact with these environments and perform kind of skills-based tasks of setting up a simulation, running the simulation, plotting the results, but also doing some interpretation and recommendation of next steps. So finally, one last example, which is even more difficult. I gave it some data from a cell phone battery from the Google Pixel 10, cycling at different C rates. So the chemistry is some kind of graphite MMC. We're not exactly sure. Attached a picture of the cell and gave it the nominal capacity along with some data. With a description of the rough cycling procedure, asked it to implement a P2D model with a parameter set that describes the data and shows me the voltage breakdown and the voltage plots in order to evaluate. And again, after working for a few minutes, not perfect results, but pretty good, pretty close, especially considering that there's no half cell data we're not even exactly sure what the materials inside are, really just based on rate capability cycling data. Um, Still able to get a pretty good baseline parameter set as a starting point. And asking the agent to evaluate its own work, it gave this bullet point response here to say, well, the low rate voltage level suggests that the positive electrode OCB is not fully representative of the real cathode. So we can feel fairly certain that it's graphite, but we don't know what the cathode is. As the C rate increases, the mismatch becomes more polarization driven, so your kinetic, diffusion, and transport parameters are not fully tuned. Also correct. The model captures rate dependence, but not the exact transition from equilibrium domination to transport dominated behavior. And if I want to improve this, I should do slow quasi-OCB, half cell OCB, and HPPC GITT pulses to extract out the results. So I think the main takeaway is that results that agents are able to give in these kinds of environments are certainly not perfect at this point, and can definitely be improved. But when we look at the ways that they're able to interact across systems, the ways that they're able to respond to complex queries to still build up relatively accurate models and data processing is, I think, something that's powerful in a way that that is going to change how we do battery simulation and battery digitalization moving into the future. And I think it's not even entirely clear what kind of doors that this will start to open. But I hope that at the very least it's going to lower the barrier for battery simulation tools to start being used more in engineering workflows and more in experimental workflows, to hopefully get battery simulation away from being a kind of artisanal thing that you really were required to get in and write Python code and understand these things, and instead be able to be a more natural interface to say, hey, I got this result that I don't entirely understand. You know, let's do some simulations and try to improve it. And I think that the door to that is open. And as more data starts to become available, as more infrastructure starts to be built out, the future is wide open for that. Yes, and pretty pictures to close. So not only voltage curves, but we can also look into the state variables profiles to see how lithium concentration varies in the different regions of the electrodes, and based on that, the agent can then also make predictions to say of the variations that we see, of the over voltages and the deviations from open circuit potential. What are the mechanisms that are driving these observations, and then working in conjunction with the researcher, try to design better tests to explore that further. So the future is wide open. I think it's really exciting time to be working at this interface between agents and digital infrastructure and experiments. And I think the remainder of this year and the next few years are going to lead to some interesting developments in that regard. So thank you to all of our collaborators who work on these topics. Thank you to the European Union for funding this work, especially through projects like DigiBat and Battery 2030 Plus. And thank you to you for your attention. I hope it was interesting. I hope maybe you learned something new. And if you have any questions, I'm happy to discuss.